Okay, so this is a video comparing Kekule's model of benzene to the delocalized model, and also looking at some evidence for why Kekule's model was incorrect. So first of all, Kekule's model is called a resonance model. So what do I mean by resonance? So if I can ask you, if you're watching this, and just do this, just go with me, if you can just stand up for a second. Actually, if you could just sit down. Actually, if you could just stand up again. Actually, if you could just sit down. Okay, we'll stop there. What you was doing then is you was resonating. When you were standing up and sitting down, you was flicking between two different states. That's called a resonance. Now, in Kekule's model, benzene wasn't standing up and sitting down. What was happening is the double bonds were changing location. So the story goes, I never know whether to believe these or not, but so the story goes, he had a dream about a snake eating its own tail. And so he thought, well, maybe benzene is a cyclic molecule with 3 double bonds. So it would be a triene. And then what happens is the double bonds can kind of spin around the ring, like so. So you can see rather than being in this location, they're now in that. Rather than this one, they're there. Rather than that one, they're there. And then that can also spin back again. So it can flick between these two different states. It can resonate between these states. So that's what Kekule believed, and everyone was like, oh, Kekule, you're the man, well done. And so, you know, for ages, this is what we thought. But then certain evidence started to come into light, which suggested that actually Kekule's model is not the correct model. And one of those bits of evidence is the enthalpy of hydrogenation of benzene. So what is the enthalpy change when you add hydrogen to benzene? Now, loads of people had already done this first one in the lab loads of times. It was very well known that if you take an alkene, so cyclohexene, and you hydrogenate it, so you can just have a little think about what catalyst we'd need for this. Be a nickel, wouldn't it? Yeah, to hydrogenate an alkene takes a nickel catalyst. Experiments were done. It was found it took minus 120 kilojoules per mole to do that. So Kekule had a prediction, and that's what science is about. It's about coming up with a hypothesis. He hypothesized it was the resonance model, and then figuring out an experiment to check whether your hypothesis can make accurate predictions. That, in a nutshell, is what science is. So the hypothesis was, well, if Kekule's model has 3 double bonds, it should take 3 times as much energy. So the prediction was the enthalpy of hydrogenation of benzene would be minus 360, minus 120 times 3, because you're not breaking 1 double bond, you're doing 3. However, when we did the experiments with actual benzene, it turned out the number was minus 208. Now, you don't need to memorize any of these exact numbers. All you need to remember is the actual enthalpy of hydrogenation was less negative than what Kekule predicted. Okay, so in like a sentence, the first bit of evidence to disprove Kekule was that the enthalpy of hydrogenation of actual benzene was less negative or less exothermic, if you like, than what Kekule predicted. Okay, so you know, in terms of the scientific model, that's not good so far. His hypothesis did not agree with experiment. Kekule also made a second prediction. In his model, it doesn't matter which resonance you look at, either way, you have 3 carbon-to-carbon single bonds and 3 carbon-to-carbon double bonds. Now, a carbon-to-carbon single bond has only got 2 electrons pulling those nuclei together. Kind of looks like this. Here's the nuclei, the carbons, here's the electrons, right? A bond is 1 pair of electrons. And so as you've only got 2 electrons pulling the nuclei together, this is going to be quite long because there's only 2 electrons pulling them in. Now, in a double bond, you've got 4 electrons, 2 pairs, pulling those nuclei in. And so that's going to pull the nuclei closer. Your carbons are going to get closer together because there's a greater attraction from the electrons. And so this bond will be shorter than the single. So Kekule's prediction, based on his hypothesis of the resonance model, was that there will be 3 long and 3 short bonds. Now, a lady called Catherine Lonsdale did some really interesting experiments using something called X-ray crystallography, which is a really interesting technique. I would advise looking it up online and just spending 10 minutes finding out about it. It is a really useful and interesting technique, and it lets you look at things that are incredibly small. And so small, in fact, she could actually use X-ray crystallography to measure the actual bond length in benzene. And it turned out all of the bond lengths, the carbon-to-carbon bonds, were equal. They're all the same. But that doesn't fit Kekule's model. So again, that's another bit of evidence that Kekule was wrong. His hypothesis did not meet the experimental results. Okay. And then very finally, we had a third bit of evidence. So if we took an alkene, and Kekule's model was just a triene, wasn't it? So a double bond, and we try to halogenate it with a Cl2, it's going to happen, that will work, it'll actually happen really quick, and you'll get a product. Just stop the video, have a go at drawing out the product. Once you've done it, press play again, and I'll go through the answer for this top one. And any conditions or anything as well you think you need. Welcome back. So you actually don't need any conditions for this. As I said earlier, this just happens really quickly. This is electrophilic addition. If you remember that from the alkenes topic, we're going to break the double bond. A Cl will go on the first carbon that had a double bond, and the other Cl will end up on the second carbon that had the double bond. And as we said, this mechanism, if you remember your alkene stuff, is electrophilic addition. Now, all Kekule's model is a triene, so you'd imagine Kekule's model would also react with chlorine. However, if you look at actual benzene, when you try and react it just with chlorine and nothing else, it won't react. And that's because actual benzene cannot do addition reactions. So it can't use this mechanism. Now, if you've been getting a little bit ahead and looking at the reactions benzene can do, there is a way to make benzene react with chlorine, and the answer is you'd add a halogen carrier as a catalyst. However, it wouldn't be an addition reaction. That would be electrophilic substitution, which is different. So the third bit of evidence is that benzene will not perform certain reactions, specifically addition, that Kekule's model would, being an alkene. Okay, so to summarize that, we have the enthalpy of hydrogenation of actual benzene is less exothermic or less negative than what Kekule predicted. The carbon-to-carbon bond lengths in actual benzene are all an equal length, whereas Kekule predicted 3 long and 3 short, as you have 3 single and 3 double. And benzene does not undergo certain reactions, and you can name addition as an example, which alkenes would, so that Kekule's model would. Okay. So what is the actual model then? Well, if I draw out the skeletal formula of benzene, I'll try and draw my hexagon as neat as I can. And I'm going to try and draw it 3-dimensional. So I'm going to try and draw this bit a little bit closer. So it's like coming out the page towards you. In this, each of these carbons is only bonded to 1 hydrogen. So the formula of benzene is C6H6. So each carbon only has 1 hydrogen. So if I look at, for example, this carbon here, it's making 2 bonds to other carbons and 1 bond to a hydrogen. That's 3 bonds. But carbon has 4 electrons in its outer shell. So we have a 4th electron that is not being used to make a bond. And that will be in a p orbital. So just have a little think, try and remind yourself, what does a p orbital look like? What shape does it have? Okay, so it is like a dumbbell shape. So each of these carbons, so I'm trying to do this as neat as I can, my handwriting isn't the best. They're supposed to be equal sized dumbbells there, not too bad. And so we have them some pointing up and the other half pointing down. And in each of these p orbitals will be 1 electron. That's where that 4th electron goes from each of the carbons. So in total, there's 6 electrons in these p orbitals, 1 per p orbital. Now what happens in benzene is kind of like in an alkene. So if I just had carbon to carbon with a single bond, and then we have a p orbital on each of them, in an alkene, the p orbitals can overlap side on, can't they? And we get like a little hot dog bun. So I always imagine the single bond is the sausage, and then this is the pi bond. Together, these would make the pi bond, and then the black would be the sigma. So that's what happens in an alkene. In benzene, exactly the same thing happens, but with all 6 p orbitals. So we don't end up with a pi bond, so to speak, we end up with a pi system. It's like bigger than a pi bond. And so all 6 of these top lobes, I'm just going to shade in the top ones. All 6 of those shaded in ones, they all overlap together, just like in an alkene, and we get this ring above the plane of the carbons. And notice I've given my ring thickness. So it's not just like that, it's not a circle, it's a ring, it's like 2 circles. And then all 6 of the bottom lobes also overlap underneath the plane of the carbons. And so what we end up with is a delocalized ring of electrons. Now, technically it's 2 rings, but this is all part of the same pi system. I'll write that down. So this is a delocalized pi system. And where would we describe where the system is? It is above and below the plane of the carbons. If you need to explain what the delocalized model of benzene is, that's your explanation. It's a delocalized pi system. Why is it delocalized? Because the electrons can go anywhere they want in these rings, so they're not stuck in one place, they're delocalized. It's a pi system, not a pi bond, because it's caused by more than 2 p orbitals. It's caused by 6. And clearly you can see it's above and below the plane of the carbons. Okay, now, as amazing as my diagram is, I'll show you an actual model. Here's a model of that delocalized pi system. Each of the black ones is the carbon. You can see each carbon is bonded to a hydrogen, that's the white stick. And then these white polystyrene bits, that would be the sigma bond. So each carbon is making a sigma bond, a single bond to each. And then obviously the green is the delocalized pi system above and below the plane of the carbons. So it looks like that. Okay, a bit more complicated than what you might first imagine. Okay. So we'll call that there. Thank you very much. Have a nice day.